Ensuring network and recovery. We'll explore why network performance and recovery are critical to reliable IT services. In this presentation, we'll cover how to keep networks reliable, optimize performance, and recover quickly from failures. We'll start with collecting and analyzing network data, move into managing traffic, then plan for recovery, and conclude with key takeaways. One way we keep services reliable is through effective network management. Network management enhances efficiency and prevents downtime. Network management is all about keeping the network healthy and running smoothly. That means controlling who has access, checking for hardware issues, making sure critical apps get the bandwidth they need, keeping track of equipment and configurations, and timing upgrades so they cause minimal disruption. The goal is simple: boost efficiency, prevent downtime, and catch problems before they happen. A key piece of network management is knowing what's happening in your environment, starting with environmental monitoring. Environmental monitoring protects network equipment and performance. Environmental monitoring keeps a close eye on the physical condition that can impact network performance. Things like temperature, humidity, airflow, power, smoke, flooding, and even unauthorized access. Sensors feed this data into a central system, which alerts administrators when something's outside safe limits. Tools like Room Alert, EnviroMux, and PRTG provide that real-time insight, helping you stop small environmental problems before they turn into outages or hardware damage. But protecting the hardware is only part of the picture. We also need to see exactly what's happening inside network traffic. Traffic monitoring tools provide visibility into network health. Traffic monitoring helps spot performance issues and security threats before they spiral. There are three main ways to capture that data: wireless monitoring in promiscuous mode, inline monitoring using a TAP, traffic access protocol, and switch port monitoring. Once you have the data, tools like Wireshark can dig into the packets, while SNMP and NetFlow give you a broader view of devices and traffic patterns. Together, they make it much easier to detect anomalies or even malicious activity early. Traffic data isn't the only source of insight. Event logs and syslog can tell us a lot about what's happening on our devices. Monitoring protocols capture and analyze network traffic to detect issues and improve performance. Monitoring tools don't just watch traffic, they make sense of it. They can capture data, replay network conditions, and highlight errors that point to trouble. For example, runts are packets that are too small, giants are too big, and jabber happens when a device sends abnormally long packets, often from a bad NIC, or network interface card. Ghosts are malformed packets from faulty hardware. You might also see packet loss from congestion, discarded packets from errors or full buffers, and interface resets from faults or configuration changes. Spotting these patterns early helps you fix issues before they impact users. Alongside packet analysis, event logs and syslog show us what devices are actually doing and why. Event logs and syslog provide insight into device behavior and security events. Event logs and syslogs are like black boxes of your network. They record what's really happening. Windows Event Viewer captures local system events, while syslog provides a universal format for logs from routers, switches, servers, and other devices. Those messages go to a central collector, making it easy to review and audit activity. With them, network administrators can spot configuration errors, detect unauthorized access attempts, and troubleshoot problems faster. To go even deeper, tools like SNMP and NetFlow reveal overall traffic patterns and usage. SNMP and NetFlow provide network-wide monitoring and traffic pattern analysis. SNMP, or Simple Network Management Protocol, is like giving your devices a regular checkup. It polls them for real-time health statistics, CPU load, interface errors, and uptime, so you know how they're performing. NetFlow, on the other hand, is the traffic detective. It watches where packets are coming from, where they're going, and which apps, users, or protocols are hogging the bandwidth. Together, they give you both views. How healthy is the network? the checkup, and what's consuming our bandwidth, the investigation. This combination is critical for planning capacity, spotting security red flags, and fixing performance issues before they snowball. Now that we can see what's happening across the network, the next step is to control how traffic flows. Managing network traffic ensures reliable and efficient services. Managing network traffic is all about making sure devices and links keep up with demand while quickly spotting and fixing problems. We do this with tools like baselines to define normal, bandwidth allocation to prevent bottlenecks, flow control to keep data moving smoothly, congestion prevention to avoid slowdowns, and QoS, or quality of service, to make sure critical services get priority. Together, these strategies keep the network fast, stable, and ready for anything. Of course, you can't manage what you don't measure, so the first step is building performance baselines. Performance baselines define normal to detect changes and problems. A performance baseline is your network's normal. It tracks things like utilization, user counts, protocol mix, and error statistics, so you can quickly spot when something's off. Without one, you're basically guessing. Tools like iPerf or full-featured monitoring suites gather key performance indicators such as uptime, interface performance, error rates, packet loss, and jitter. These baselines aren't just for troubleshooting, they also guide capacity planning and upgrades. Once we know what normal looks like, we can fine-tune bandwidth and device capacity to keep things running smoothly. Bandwidth management optimizes traffic volume and device capacity. It's all about keeping traffic flowing without overwhelming the network. Since not all devices have the same capacity, we use tools to balance the load. Flow control keeps data moving at a rate devices can handle. Congestion control helps the network adapt when it's busy. And quality of service makes sure critical traffic, like voice and video, gets priority even during peak usage. Let's start with flow control, how we can keep traffic balanced between endpoints. Flow control prevents receivers from being overwhelmed. Flow control prevents a receiving device from being overwhelmed by more data than it can handle. It works at the data link or transport layers using two main styles: rate-based, which caps how fast data is sent and drops the excess, and feedback-based, where the receiver signals the sender to slow down. Three common methods are shown here. Stop and wait, send one frame, wait for an acknowledgement. Simple but slow. Go back in, sends multiple frames, but resend the whole batch if one is lost. Selective repeat, only resend the missing frames. This saves time, but needs out-of-order handling. These techniques keep devices stable and prevent packet loss when things get busy. Flow control manages traffic between two devices. Congestion control manages load across the whole network. Congestion control prevents and remedies excessive network traffic. Flow control manages traffic between two endpoints, while congestion control addresses overall network load. We use two main strategies: open loop and closed loop. Open loop strategies prevent congestion before it starts. Retransmission policy controls how lost packets are resent. Window policy tunes sliding window sizes. Acknowledgement policy reduces extra acknowledgements. Discarding policy drops low priority packets. And admission policy blocks new flows when capacity is near. Closed loop strategies respond after congestion begins. Implicit signaling detects delays or missed acknowledgements. Explicit signaling marks packet headers. Choke packets tell senders to slow down. Back pressure pushes warnings upstream. Used together, these techniques keep traffic flowing and performance stable. Next, we'll see how QoS gives critical traffic the VIP treatment it needs to stay reliable. QoS, quality of service, ensures critical traffic gets priority for reliable performance. QoS makes sure important traffic, like voice calls or video streams, get through smoothly without delays, jitter, or packet loss. It does this with traffic shaping, policing, and prioritizing by protocol, IP addresses, VLAN, user group, or application. At OSI Layer 3, diffserv marks packets for priority handling. At Layer 2, class of service, COS, tags Ethernet frames to specify priority. Together, these techniques keep essential services steady even during heavy congestion. But QoS isn't always used fairly. Some ISPs have been accused of throttling or favoring certain traffic, sparking net neutrality debates over whether all internet traffic should be treated equally. Monitoring and traffic control are proactive measures, but we also need a plan for when things go wrong. That's where response and recovery come in. Response and recovery strategies minimize chaos and speed network restoration. A strong response and recovery plan can turn a disaster into a manageable problem. Preparation cuts confusion and helps teams make quick, smart decisions. Incident response tackles localized problems like breaches or hardware failures. Disaster recovery steps in for large-scale outages, and with backup, power, and data restoration, you can bring systems back online faster. In short, preparation plus planning equals less chaos and a quicker return to normal. The first step in that planning is incident response, stopping problems before they spiral out of control. Incident response plans reduce chaos and speed recovery. An incident response plan spells out what counts as an incident and exactly how to react. The goal is simple: protect people, data, and uptime while learning from every event. It follows 6 key stages. Preparation: have people, procedures, and tools ready. Detection and identification: spot and escalate problems quickly. Containment: isolate effective systems to stop the spread. Remediation: fix the root cause, not just the symptoms. Recovery: restore operations to normal. And review: document what happened and improve for the next time. Handled well, this process keeps incidents from turning into disasters. Part of that response is making sure critical data is preserved, especially when legal compliance is on the line. Data preservation ensures evidence remains admissible and reliable. When an incident happens, preserving data is key to keeping evidence admissible and trustworthy. That means locking down the area, documenting what you see, monitoring how evidence is collected, protecting the chain of custody, tracking its transport, and writing a thorough final report. Follow these steps, and you'll protect the integrity of your investigation. When problems go beyond isolated events, disaster recovery planning keeps the business running. Disaster recovery planning ensures business continuity after major disruptions. Every business needs a plan for worst-case scenarios: natural disasters, cyber attacks, even sabotage. A business continuity plan, or BCP, outlines how to keep operations running. Within it, the disaster recovery plan, or DRP, focuses on restoring critical IT systems and data. That means naming emergency coordinators, defining backup methods and locations, building network redundancy, and setting up communications that work, even if normal channels fail. And it's not just writing the plan. Regular testing keeps it effective. A strong DRP shortens recovery times and reassures both customers and insurers that you're ready for anything. That includes deciding where to operate if our primary site is down, through contingency recovery sites. Contingency disaster recovery sites provide varying speed and cost trade-offs. Disaster recovery sites differ in how fast they can get you running and how much they cost. Cold sites are just lease space with basic hardware. They're cheap but slow to set up. Warm sites have partial configuration and some current data, faster but pricier. Hot sites are fully mirrored and ready for instant failover, fast but expensive. DRaaS, or Disaster Recovery as a Service, uses cloud platforms like AWS or Azure for scalable, often lower cost recovery, but though it depends on a solid network connection. A rule of thumb: the faster the recovery, the higher the cost, unless you use flexible cloud solutions. Even the best recovery site is useless without reliable power, so power management is critical. Reliable power management prevents downtime and equipment damage. Power problems, Surges, noise, brownouts, and blackouts can wreck hardware and knock services offline. Surge protectors and PDUs keep distribution clean, while UPS systems provide instant backup. Standby UPS units kick in only during an outage. Online UPS units run equipment through the battery at all times, smoothing out every fluctuation. And for long outages, backup generators keep things running. Together, these measures protect gear and keep your network alive when the lights go out. Finally, robust backup systems protect critical data and speed recovery after outages. Reliable backup systems protect critical data and ensure fast recovery after outages. First, decide what to back up: user data, configurations, compliance records, and etc. Then choose the methods: the cloud for offsite safety and local hardware or software for fast restoration. Use full, incremental, or differential backups as needed. Schedule them frequently and verify them with test restorations. Follow the 3-2-1-1 rule: 3 copies, 2 media, 1 offsite, 1 offline, and design backups to meet RTO, or recovery time objectives, and RPO, recovery point objective, goals to make sure your backup design matches your organization's tolerance for downtime and data loss. Putting all together, proactive monitoring and planning keep networks reliable and resilient. To wrap up, proactive network monitoring and well-planned recovery strategies ensure reliability and resilience. We've looked at how to monitor networks, manage traffic, and prepare for incidents and disasters. You now know how to collect and analyze network data, prioritize critical traffic, and respond quickly to both small disruptions and major outages. Strong backups, solid recovery plans, and regular testing tie it all together. The takeaway: monitor, plan, and test so your network stays ready for anything. And with that, we've got the tools and strategies to keep our networks running no matter what's thrown at them. Thank you. Here is a list of references used to prepare this presentation. Thanks for viewing the video. I'll see you on the next one.